There's only one more law we need to talk about for this chapter, and that is Dalton's law of partial pressures. And this says that the total pressure of a mixture of gases is equal to the sum of the partial pressures of each component gas. So if you're taking the notes, go ahead and pause the video and write this definition down, and then we'll talk about it. And basically what it's saying is that if you have one balloon with a pressure of, say, 1 atm, and you have a second balloon with a pressure of 2 atm, if you put those two balloons together into one balloon, then the total pressure would be 3 atm. So basically you just take the partial pressures, which is just the pressure from one thing, and you add them together to get the total. So our equation looks like this, where the total pressure is equal to each individual pressures added up together, for however many pressures you have. And the definition of partial pressure, just so you have that in there, this is the portion of the total pressure that's contributed by a single gas. So if we go back to our example where you have 1 atm and 2 atm and you put them together to make 3, 1 atm is the partial pressure of the first gas. 2 atm is the partial pressure of the second gas. So this law is really easy. You just add up the partial pressures to get the total. The only confusing part is if they ever say collected over water. So let's talk about that real quick. If you collect a gas over water, the problem is you also have water vapor on top of the water. So in order to get the pressure of just the gas, you have to subtract out the water vapor from the total. And they don't actually call it the total in the question, they'll call it atmospheric pressure. And the problem with water vapor is that it's dependent on the temperature of the water. So remember, water vapor is that little pocket of gas that sits right on top of any sample of water, because at some point all the water molecules are going to try to evaporate. So since they're always evaporating on the surface, you're going to have a little pocket of gas of water right on top of it. So your total pressure is the atmospheric pressure. You're studying a sample of gas that's sitting on top of water, and since the water is evaporating, you also have water vapor on top of it. So the water vapor pressure will be given to you, but the problem is it's based on the temperature of the water. So the hotter the water is, the more it's going to evaporate. So in the question, you're going to see a temperature because the pressure of the water vapor is dependent on that. But notice the temperature is not even in this equation, and that's why it's a little bit confusing. Let me show you what I mean. If you look at this question, it looks long and complicated. It's really not. What I want you to do is notice the phrase collected over water, and I want you to highlight that phrase or underline that phrase. Whenever you see those three words, collected over water, you need to think, okay, it's just a simple subtraction. You need to find the total pressure, which is called atmospheric pressure. So in this case, it's 765. And then find the pressure of the water vapor. In this case, it's 23.8. And all you have to do is subtract the water vapor from the total to get the pressure of just the gas. So this is our total. We got the pressure of the gas plus the pressure of the water vapor. The reason this is confusing is because it gives you this temperature right here, and people try to plug in the temperature somewhere. So just keep in mind that if it says collected over water, you're not going to use that temperature. So it's basically just a subtraction, 765 minus 23.8. And there's some practice problems for Dalton's Law on worksheet number 10. So try a few on worksheet 10, and that is it for this chapter. You have now finished the kinetic molecular theory and gases.